and welcome back. In the last video, I defined isometries. These are transformations of the plane which don't change distance between points. In that video, we started looking at some simple examples of shapes which had symmetries. That is, shapes which are not changed when you apply some isometry. And hopefully you've played with a few more examples when looking at the exercises. In this video, we're going to explore isometries in more detail. There are several different types of isometries. We've seen examples of translations, rotations, and reflections. You might wonder if there are any other types. It's quite likely that you've learnt about at least one more, glide reflections. They are combinations of a translation and reflection. A nice example of a pattern which has a glide reflection as a symmetry is footsteps in the sand. If you translate by the length of a single pace and then reflect in the line they're walking along, the footsteps line up with each other. There is one other type of isometry that you might think is a bit silly to include, but turns out to be very important. Think about the transformation of the plane, which sends each point to itself. It does nothing. Well, clearly the distances between points don't change because none of the points are moving. So this is an isometry by our definition. You could call it a rotation by 0 degrees or a translation by a distance 0 if you wanted to, but it ends up being helpful to think about it separately from the others. It even has a special name, the identity. There is now a little bit of linguistic gymnastics to do. Clearly, the isometry is a symmetry of every shape because it leaves the shape looking the same. But we don't want to declare that every shape is therefore symmetric. We just need to tweak what we mean by symmetric and say that a shape or pattern is symmetric if it has a non-trivial symmetry. That is, a symmetry which isn't the identity symmetry. I want now to draw a connection between isometries and a concept from geometry with which you should be familiar. Remember that we say two triangles are congruent if their sides have the same lengths. There is a similar notion of congruence for other shapes in the plane. Well, suppose we have two congruent triangles. It's obvious that we can transform one into the other, maybe by translating and rotating one until it lies on top of the other. In short, it's obvious that if you have two congruent triangles, there is an isometry which sends one triangle to the other, since both triangles have the same side lengths. There are two things that we can get from this observation. The first is that actually the idea of congruence is exactly captured by isometries, because two things are congruent if they are the same shape and size, and an isometry is a transformation which doesn't change distances, and therefore doesn't change shape or size. It makes sense, therefore, to just define one in terms of the other. We say that two shapes or patterns are congruent if there is an isometry which exactly sends one onto the other. The advantage of this definition is that it works for all shapes and patterns at the same time. The second observation is a subtle but, again it turns out, important one. If two shapes A and B are congruent, there is an isometry which sends A to B, but also there is an isometry which sends B to A. This suggests that we might be able to undo isometries. If we apply the first isometry, sending A to B, and then the second one sending B to A, they may cancel out and we end up where we started. Be careful, because we don't yet know that this is always the case, because we're only saying something about the shapes A and B and we don't know what the isometries do to the rest of the plane. But clearing this up is the main point of this video. If the two isometries do cancel each other out, we say that the isometries are invertible because they undo each other, and we say that they are inverses of one another. We have been presented with the question of working out when two isometries are the same. To say that one isometry undoes the other, or is the inverse of the other, what we mean is that every point is sent back to where it started, or in other words, the result of doing one isometry followed by the other is the identity isometry. How can we tell, given two isometries, whether they are in fact the same? An example which comes to mind is the following. You may have seen a reflection in a point, or an enlargement by scale factor -1. This is a transformation of the plane which sends each point to the one opposite it across a chosen centre of enlargement. If you've seen this transformation before, you may recognise that it is another example of an isometry, but it also has the same effect as doing a rotation by 180 degrees centred at the centre of enlargement. This means that it's not really a new isometry, but it isn't easy either to see that it is the same as a rotation. So the question is not a trivial one. It turns out that there is in fact a quite beautiful and simple answer to the problem. It takes the form of the following theorem. Theorem: given two labelled congruent triangles ABC and A'B', there is a unique isometry which sends A to A', B to B', and C to C'. We know that given the congruent triangles, there is at least one isometry taking one to the other, and this theorem says that in fact there is exactly one. This means that if two isometries send the same labelled triangle to the same labelled triangle, they are the same isometry. As a triangle is completely defined by its vertices, we actually just need to check that the two isometries send 3 points to the same 3 points, as long as those 3 points aren't in a line. Let me now prove this theorem for you. We're going to do what is called a proof by contradiction. That means that we will make the assumption that the theorem is not true, and from this derive a contradiction or absurdity. It will follow that our assumption must have been wrong and that the theorem must be true. The theorem says that for any pair of congruent triangles, there is exactly one isometry taking A, B, C to A', B', C', respecting the labelling. To the contrary, let us assume that there is a pair of congruent triangles which can be matched up by at least two different isometries. Call them R and S. Since they are different isometries, there must be at least one point which gets sent to different places by R and S. Call this point P and say that R sends P to PR and S sends P to PS. Both R and S are isometries, so they must preserve the distance between points. Therefore, the distance between A and P must equal the distance between A' and PR, as well as the distance from A' to PS. Since A' is equidistant from PR and PS, it must lie on the perpendicular bisector of PR and PS. We can do the same trick with the point B. The distance from B to P must be the same as the distances between B' and PR and B' and PS. Therefore, B' also lies on the perpendicular bisector of PR and PS. Finally, exactly the same thing is true with the point C. So C' lies on the perpendicular bisector of PR and PS. But this means that A', B', and C' all lie on the same line, which means that they don't form a triangle. But we started off by saying that A', B', C' was a triangle. This is a contradiction, and it means that our assumption was wrong, and therefore that the theorem is true. We can use this theorem to check what I said earlier, that an enlargement by scale factor -1 is the same as a rotation by 180 degrees. We just need to check 3 points, say these 3 points. Under the enlargement, they get sent to these 3 points, while under a rotation, they get sent to these 3 points. The points are the same, so the theorem tells us that the isometries must be the same. Let me give you a couple of words of warning. First, let's try and apply the theorem using these 3 points. A translation sends them here, but so does a glide reflection. So there's no unique isometry sending the first 3 points to the second 3 points. But the reason this doesn't work is because the points form a line, not a triangle, so the theorem does not apply. Secondly, look at these 2 congruent isosceles triangles. We can send one to the other by a translation, but also by a reflection. This time notice that the labels get messed up in the second case. A gets sent to B' and B gets sent to A'. In fact, this example is why the labeling is necessary. For a scalene triangle, the labeling doesn't really matter because there's only one choice for isometry anyway. Finally, let us use the theorem to sort out our original problem. Remember that just using congruence, we could find 2 isometries between 2 congruent triangles, one which sent the first to the second and one which sent the second to the first, but it wasn't clear whether the 2 isometries cancelled out. Now with the theorem we can clear up this problem. Label the first triangle ABC and the second A'B'C', and choose the isometries so that they respect the labeling. Now, doing one followed by the other, A goes to A' and then back to A, B to B' and then to B, and C to C' and then back to C. So overall, A, B and C are sent to A, B and C respectively. But we also know that the identity isometry sends A to A, B to B and C to C. Since the theorem says that there's exactly one isometry which does this, the 2 congruence isometries must combine to give the identity, so they do cancel out, and they are inverses of each other. This in fact means that every isometry has an inverse. Now you have the chance to try some exercises and think more about isometries, congruence, inverses and uniqueness. Do have a go at these because they will be helpful in understanding the rest of the course. In the next video, Albert will take over and introduce groups of isometries, so look forward to that, and I shall see you next week.